before we continue with the last example, I want to have a short discussion about the connection between absolute values and inequalities. I know that you probably already encountered this in previous pre-calculus courses, but I just want to make sure that we are all on the same page here. So imagine that we have the following inequality. The absolute value of x is less or equal than 3. And we want to be able to find all the values of x that satisfy this inequality right here. And in order to do that, I want you to remember the basic idea of an absolute value of x. The absolute value of x measures how far apart the number x is from 0 on the number line. So keeping that in mind, let's go back to this inequality here. We want to find all the values of x such that the absolute value is less or equal than 3. So then that means that what we want here are all the x values that are 3 units away from the origin, from 0, or within 3 units away because we have less or equal than 3 units, or we want all the values of x to the left of 0 up to -3. Also, because the inequality is including 3, it says less or equal than 3. That means that +3 is allowed to be part of the solution set, and -3 is also allowed to be part of the solution set. So then, as long as we choose an x value in this region, all of these x values right here are within 3 units away from 0. Similarly here, we can choose an x here, an x here, an x here, and all of these x values are within 3 units away from 0, including 3 and -3. So then, that means that as an inequality, we are really saying all x values less or equal than 3, greater or equal than -3. In proper set notation, you're going to write that the solution, S for solution, is the set of all x such that -3 is less or equal than x, less or equal than 3, where these numbers are real numbers. In interval notation, the solution set will just be everything from -3 to +3. All right, let's do something a little bit more interesting. Let's say that now you are given the absolute value of 8x less or equal than 2. And you're asking to solve the inequality. Find all the x values that satisfy this inequality. So the idea is the same as in the example that we just finished. I want you to think about the inside as a whole, not just x, 8x. What we know is that all of 8x has to be less or equal than 2, greater or equal than -2. So this is what we know. In other words, if I were to draw this on the number line, this will be 0. Let's position 2 right here. Let's position -2 right here. We are including -2. We are including +2. And what we are really saying here is that 8x, all of 8x, everything inside of the absolute value, 8x has to be between -2 and 2, so within this region. So this is why I wrote it like this as an inequality. So 8x has to be between -2 and +2. So anything in this overlapping region right here. By doing that, now I can actually solve for x. The way to solve for x, the easiest way, is to be able to divide every single side of the inequality by 8. This is perfectly legal in mathematics as long as you do it to every side of the inequality. Now in this case, the 8s will divide each other out, and here you can simplify. This will be 1, this will be 4, same thing over here, 1 and 4. And now what you found is that x has to be between 1/4 and -1/4 for this to be true. So the actual solution set, please know that this is not the official solution set of the inequality, because this is a statement about 8x. The solution set must be a statement about x. So this is the actual solution set of the inequality. So what we really have as the solution set is that for this inequality to be true, x has to be, if this is 1, let's say 1/4, x has to be between 1/4 and -1/4, including 1/4, including -1/4, and this is really where x needs to be. Okay, so x needs to be right here, everywhere between -1/4 and 1/4. So then you can now write the solution set. Oops, that's a marker. You can now write the solution set as the set of all x such that -1/4 is less or equal than x, less or equal than 1/4, where x is a real number. Or you can write it in interval notation. So then that will be everything from -1/4 to 1/4. Let's now have a third example, something a little bit with more spice. Let's say that we have to solve the absolute value of 2x minus 4 less than 5. Why not? So if we have something like this, again, I want you to see the inside as one big piece. This is saying that everything inside of the absolute value has to be within 5 units from the origin. So if I were to draw my number line right here, here is the origin. Let's say that this is 5, this is -5. Now I am not including the endpoint, so I'm going to put an open circle there. And what I really want here is practically just values that are within -5, 5. So this is exactly what is being represented by 2x minus 4. 2x minus 4 has to be in this blue region between -5 and 5. So I can write this over here as a 3-part inequality. I can say 2x minus 4 must be less than 5 and must be greater than -5. Once I do that, I can now do simple operations of addition and division to isolate x, because what I want is to have x completely alone inside. So in order to do that, I am going to begin by adding 4, but whatever I do to one side, I must do to all of the other sides of the inequality. So that's going to give me 2x inside, 5 plus 4 is 9, -5 plus 4 is -1. And now I continue simplifying by dividing every single part by 2. So that's going to give me x in the middle, 9/2 on the right, and -1/2 on the left. So then graphically, please remember that this is not the actual solution set, because this is a statement about 2x minus 4. For something to be the solution set, I need a statement about x alone. So this is my solution set. On the number line, that means 9/2 is 4.5. So 1, 2, 3, 4. Let's say if this is 5, somewhere here, I am not including that. So I'm going to put an open circle. This is 9/2 and -1/2. if this is -1 right here, so let me put it right here as an open circle. So let's say over here as an open circle, and that's going to be -1/2. And my solution region will be everything right here. This is my solution set. Numbers between -1/2 and 9/2. So in proper set notation, the solution set will be the settable x such that -1/2 is less than x, less than 9/2, where x is a real number. Or in interval notation, open brackets from -1/2, 9/2, 1/2, and open brackets, or let's say soft brackets, because 5 over here was never included. We had less than as an inequality. So then that means that we shouldn't put hard brackets, the square brackets. We should leave it as regular soft brackets. That looks like an order pair, but remember, this is really an representing this set right here, but in interval notation. Let us now briefly go over the other case where we may have greater or equal than. Imagine that we have the absolute value of x is greater than 3. So now what is happening is the following. Here is my number line. I have 0, 1, 2, and 3, 1, 2, and 3. And 3 is not being included, so I'm going to immediately put an open circle. What this is telling me now is that since I have the absolute value of x is greater than 3, the values of x that satisfy this inequality are all x values that are more than 3 units away from 0. 3 units away from 0, more than 3 units away from 0. That means that it could no longer be in this region over here because these are within 3 units away from 0. If we want more than 3, that is talking about these x values right here, all of these x values, and all of these x values on the left as well. We are not even allowed to use to include 3 and -3 because we have a strict inequality. We don't have greater or equal. We have strictly greater than 3. So because we have now this gap over here, the intervals are anything bigger than 3 and less than -3, we are not going to be able to have one single inequality. We're going to have 2 separate inequalities. One inequality will represent this interval and another one will represent that interval. So we write it like this. X is going to be less than -3 or x is going to be greater than 3. So in proper set notation, this is how you will represent it. The settable x such that x is less than -3 or x is greater than 3, where x must be a real number. And notice the emphasis on the word or because you cannot be in these 2 intervals at the same time. You are either here or you are here. The 2 intervals are separated. So this is why the word or and not and. And is whenever, let's say, you are here in the middle. But now we have this gap. So an x value can be either in this set or in this set, but it cannot be in both sets at the same time. So this is why whenever you have the 2 inequalities pointing in opposite directions, it is important to put or in the middle if you're using set notation. In interval notation, practically in interval notation, we follow the directions of the number line. And we always go from the left to the right. This is how you travel whenever you're thinking about interval notation. Coming from negative infinity, you are going to have soft brackets, negative infinity, and then remember, you're coming from the left and you're going towards the right. So you encounter now -3. This is a place where you stop. Brackets here. And then once you do that, you're going to skip all of this. You keep traveling, and now you go to 3 and then off to positive infinity. So you're going to say from 3, not including 3, to positive infinity. Now, how do you represent the word or symbolically? Symbolically, you represent that with the union symbol. This is the symbol for union. Okay? That means that you are in this interval or in this interval. So the union symbol here is representing the word or. So set notation or interval notation. And typically that will be your choice unless the question is telling you represent the final solution in set notation. Then you do set notation. If it says interval notation, you do interval notation. If it doesn't say any of the two, so that will be your choice. I could care less. They're both beautiful ways of representing an interval. Let's do one more example with greater or equal to wrap up this mini discussion on absolute value inequalities. So let's say that we have the absolute value of 3x plus 2 is greater than 4. Let's say greater or equal for a change. As soon as I see greater or equal, then I know that I am going to have this scenario of or right here. And I'm thinking of everything inside of the absolute value. This is telling me that the stuff inside has to be more than 4 units away from 0. So that means that 3x plus 2 has to be greater or equal than 4, or 3x plus 2 has to be less or equal than -4. So quickly here on the number line, here we have 0, 1, 2, 3, and 4. And here 1, 2, 3, and 4, so -4. And what we are saying is that we now want everything that is greater than 4 and less than -4. And now we are allowed to include 4 right here and -4. So practically, these are the statements that I am making over here. Now what I'm going to do is to simplify each inequality separately. So then 3x is greater or equal than 4 minus 2, which is 2. Dividing the inequality by 3, x is going to be greater or equal than 2/3. And then over here, 3x is less or equal than -4 minus 2, -6. X is going to be less or equal than -2. So on the number line, the solution set will be, this is 0. We're going to have 1 and -2 right here. I am allowed to include -2. X has to be less or equal to -2. So this set right here. And then in the other case, if this is 1, let's say 2/3 right here. So that's going to be 2/3. And x has to be greater or equal than 2/3. So this is actually the solution set represented on the number line. Now in set notation, you're going to say the settable x such that x is less or equal than -2, or x is greater or equal than 2/3, where x is a real number. And in interval notation, you're going to go again from left to right. So from -infinity to -2, hard bracket, or union, and then from 2/3 all the way to positive infinity.